How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And on today's program, our special business is the subject of energy and momentum, two of the great immutable ideas of physics. And we must make clear their difference. So, for my purpose, I go to the two cars again. You remember what we have in earlier programs: a large, massive car on wheels, and a smaller car, little m, on wheels, and they are on the tabletop, and they are connected by a sort of elastic connection of rubber bands. Now, when I pull them apart, I store some elastic energy in the stretch spring, and there is a force then which is exerted on both cars. Now, what did we learn before? We learned that the big car has a little acceleration, and the little car a big acceleration, because one and the same force acts on both cars. Now, we also saw on another occasion that the little car acquired the greater velocity, and the bigger car the lesser velocity, and we called the product of m and v the momentum. And it is not unreasonable now to say that because the accelerations are inversely as the masses, the velocities are so, and therefore the momentum of the little car is equal to the momentum of the big car. So their momenta are equal. But now watch. Watch. Is it not true that the smaller car went the greater distance? That is, if I let them come from a place of rest and meet, they would meet somewhere in here. This is the distance the big car would go, and this is the distance the little car would go. So the little car goes the greater distance, s, little s. And now I define for you what is meant by work or energy in physics. The product of a force and a distance. The product of a force and a distance. So, the same force acts on both cars, but for the big car, the distance is a little one, and for the little car, the distance is a big one. And these products are not equal. So we learn this astonishing thing, that although the forces are the same, the accelerations are inversely as the masses, the distances are inversely as the masses, the momenta are equal, but the energies are not. Very important idea. Now, this business of energy, beautifully demonstrated as follows. Look what we have here. Here is a curved track, straight and short here, straight and long here. Now this end of the track is at the very same elevation above the tabletop as this end. I have shimmed it up on that end to get it horizontal. And what do? We put a ball at the top of this track at this end. It has so much potential energy, being so high above the zero potential plane, and I let it go. Now it is losing some of its potential energy, gaining kinetic, losing energy really because friction is in the system, and we hear sound, which costs the ball something. It cannot produce the acoustic energy for nothing. Now what do some think? That coming down this long track, the ball down here will have enough velocity, enough kinetic energy of motion to put it up over the track here. But that is not so. If the system were absolutely ideal, no friction at all, which is impossible, the best the ball could ever do would be to go to the same height here. And since we are in a real world and friction plays a large role, the ball can never go as high on that end as I let it go from on this end. Watch it. Oh, it did. I'm glad it did, because I said it wouldn't. So somebody says, Professor, The experiment failed. No, I think what I have done, I manipulated this end a little improperly so that this end is higher, and therefore it did what it did. So you see, a lesson to be learned. Experiments never fail. I'm going to lower this a little, and now I hope that this end is the same height as that. Now watch it. Oh, that's it. And less, and less, and less, and less, and less, and so on until the energy of the system is spent in friction and in producing sound and in vibration. A very beautiful demonstration, a device which I call my energy track. Now, let's consider this business of energy further. Here is a block of wood. Here is a nail. I drive the nail into the block of wood. Oh, says somebody, what kind of physics is that? Astonishing physics. Why? I am doing work on the nail. The nail is doing work on the wood to separate its particles. And when work is done, when it is done against friction forces, heat energy always arises. Heat is a necessary consequence of work done against friction. It's proof. I'm going to pull that out. Oh, what do I feel? Too hot to handle. Accordingly, the work I did on the nail has been commuted to friction. Now, there are several kinds of energy. Several kinds which we need to consider. Mechanical energy. Mechanical energy. Thermal energy. I just showed you that with the nail heated by driving it in. While we're talking about thermal energy, here is some popcorn. Some popcorn. Now you know that if you apply thermal energy to the popcorn, it soon, as a result of this application of thermal energy, of heat, explodes. Why? Because we gave energy to the little bit of water in the droplet, in the kernel of corn. It expanded enormously. How many times does it expand? Fantastic. 1,700 times. Isn't that fantastic? No wonder the kernel explodes with a rupturing force. Mechanical energy, thermal energy, acoustic energy. Sure, my vocal cords are in vibration, and that's the only reason you can hear me. I am giving rise to excitation of the air in this place, and it is falling on your eardrum and putting your eardrum into motion, and then the bones in the ear, and finally the impulse gets to your brain. Acoustic. Magnetic energy. Electrostatic energy. Electrostatic. Let me show you that, because it is absolutely exciting. Watch this. Watch. I have here some cork dust, which I put out on the table. Cork dust. It is lifeless and dead and inert. Here is a Bakelite hard rubber rod. Now the rod, I say, and later we will say more about it on a program on electrostatics, the rod is electrostatically neutral. I bring it near the cork dust, and what do I see happen? Answer, nothing. Seeing nothing happens is a very important thing to see. Very important. Now I am going to do some work on this rubber rod. Work, work. Now watch. Oh, mamma mia, look at that. The cork dust has been attracted to the rod. Not only that, but it's jumping off. It's jumping off. And would you believe it? This is the foundation of all of our electric science. Indeed, these television cameras could not work were this principle not uncovered. More about energy. More energy. Energy. Here is a massive weight which I have lifted above the level of the floor, the zero potential plane. I am doing some mechanical work on it. I am endowing it with potential energy. Here is a nail in a block of wood, and I release the weight. Look what has happened. It has driven the nail into the block. The heat developed here, very substantial. A toy, energy, a toy, a spring. If I do work on the spring, I store energy in the spring. There is a so-called suction cup on the bottom, and in another program I will show you that that word suction is not a good one ever to use, but I'm going to put a ball in this upper platform, push down the spring, storing some energy in the compressed spring. Now the energy is available to do work for me on the ball. When the atmospheric pressure seeps into that so-called suction cup, it will let the spring loose, and you know the consequence. Up will go the ball. There it goes. Up went the ball. And there was something else. There was some action taking place in this projectile mechanism, which bears also on momentum and energy. Consider this business of momentum. This gun is a toy, and so we need have no fear about it, but don't play with guns. Concerning momentum, if I shoot the gun holding it far from my shoulder, will it not kick very severely and hurt me? Why? The mass of the gun recoils with a certain velocity, the M and the V constituting a certain momentum. How do you avoid this kick? You hold the gun tightly against your shoulder so that when the gun recoils, you and the gun constitute a larger mass and therefore less recoil velocity. An excellent demonstration of momentum conservation. Consider a toy made for 3-year-olds. Here is a little toy, a teddy bear mounted on an elastic shaft through his shoulders. He stands in a vertical plane because his center of gravity is below his axis of support. And now what am I going to do? I rolled him away, and he rolls back. And so I am demonstrating a profound principle of physics in a toy for 2-year-olds. We stored some elastic energy. It was now available to do work on me to return the car. Or such a toy. An array of geared wheels and a shaft, and some feelers in there which rub against other things and produce heat from friction. And notice, I am showing the transmutation of mechanical work into thermal energy as well as into light, because when bodies get hot enough, they become incandescent. Energy, momentum, very important. Now, as one views the history of this subject, I invite you to study it yourself, because for 150 years, there was much dispute on the difference between MV and MV square, which was settled by a Frenchman named D'Alembert. But who gave rise to the problem in the first place? A young Dutchman by the name of Christian Huygens. And I want to show you a picture of him as a little boy at the age of 11, an enchanting little rascal. And I shall have more to say about him sometime on a program on light, because he spent his youthful days throwing pebbles into the canals in his native Holland and watching the ever-growing circles of disturbance, and thus was led to the idea of the wave motion of light. And here, finally, is a picture of him in his later days with his what shall we call it, wig. Now, the idea of momentum must be clearly distinguished from the idea of energy. And I thank you for your attention.